This week, it's more fun playing with some basic meteorological concepts using MetPy as a problem-solving and exploration tool. We're going to look at wet bulb temperatures, Norman's rule, and how to plot these things on a Skew-T as well as solve them numerically. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, we're going to look at another set of thermodynamics problems, namely, how can we take a wet bulb temperature measurement, and a pressure, and calculate what the dew point is. So you may remember from thermodynamics that we can do this mathematically with not too much trouble, but we can also use something called Norman's rule, which is a graphical way using a Skew-T. And we will do that in this MetPy Monday as well as the numerical solution. But first, of course, we're going to need imports. I'm going to import NumPy as MP, import metpy.calc as mpcalc, import matplotlib.pyplot as plt, from metpy.plots, import the Skew-T object, and from metpy.units, we're going to import the units registry. That's pyplot. There we go. Okay, so first I'm going to, of course, define everything as variables. A handy thing using units is we're not going to have to worry about these being in different units like we would in a problem set by hand. So we've got degrees Fahrenheit for our temperature, 72. Wet bulb temperature, and the station pressure. Now, MetPy does have a way to go the other way. We can get the wet bulb temperature from temperature and dew point, and that uses Norman's rule as well. But we're going to do this just straight up mathematics, and then we're going to turn around and plot it on a Skew-T, because I personally find that Skew-Ts give me a better understanding of the process that's happening. Okay, so the first step is I need to calculate our relative humidity, which we can do as relative humidity from wet psychometric. If we look, it takes the pressure, the dry bulb temperature, and the wet bulb temperature. We happen to have these things, pressure, temperature, and wet bulb temperature. And let's go ahead and print out the relative humidity. Okay, so 55%. Now the dew point, we can calculate, you see there are several ways, but from relative humidity, which takes a temperature and our relative humidity. We get a dew point of about 12.8 degrees Celsius. And that is our final answer. So again, we're going to be nice and put the dew point is, in this case, we'll keep one place after the decimal, 12.8 degrees Celsius. So that's great. We solved that with just a couple lines of calculation. But now how can we do it graphically? So Norman's rule says that the wet bulb temperature, you get that by lifting a parcel of air adiabatically to the LCL and then following a moist adiabat from that temperature down to the parcel's pressure. So we know then that if we start with the wet bulb temperature and follow that moist adiabat up to the LCL, then we can follow a mixing ratio line back down and get the dew point temperature. Now again, I find this really useful as a graphical calculator to give me a better understanding and an idea of how sensitive things are to small changes. But it is worth noting that what Norman's rule gives us is actually the adiabatic wet bulb temperature. Now we measure the isobaric wet bulb temperature when we're using a normal wet bulb thermometer. Almost everyone ignores this difference. It might add up to a few tenths of a degree in some of the worst case scenarios, but it is worth noting that we're actually calculating the adiabatic wet bulb temperature And we're providing the isobaric wet bulb temperature. So there's a small source of air there that could be critical depending on your application. All right, so we know that first we need to get a Skew-T. I'm going to create a 9x9 figure. And I'm going to create an instance of skew with a 45-degree rotation. And to start off with, let's just plot the data that we have. So pressure and temperature. I'm going to use an O marker, and I'm going to make that tab green. We have the dew point. Actually, let's make that tab green. And let's make temperature red. Doesn't really matter, but a little bit more convention. And our wet bulb temperature. We'll make that tab olive. And don't forget to put our marker in here. Now, yes, I am plotting the dew point, which is what we're looking for. We've already calculated it. But in this case, I'm going to plot everything so we can see how Norman's rule works. Obviously, it's a little harder to trace on your screen and do this, but I think this gives you a good understanding. And if I were teaching Norman's rule, I would certainly make this plot in a couple of stages and progressively build the answer up on a slide. All right, so let's make sure that our code is going to work. And we see that we have a dew point, a temperature, and a wet bulb that's in between them. So that's great when it's actually quite a ways towards the dew point here. Okay, I'm going to set some limits. I'm going to get the axis object from Skew, call set xlim from 10 to 30, and ylim from 1040 to 800 HPA, just to get zoomed in a little bit more here on our area that we're interested in. All right, I'm going to create a pressure plot array using arange, and that's going to go from our pressure that we're starting at, which we know is our station pressure, up to 800 in units of -1, and we need to assign hectopascals to that. And this is just why I'm going to calculate our different lines over the pressure range and plot them. So now we'll do the dry adiabat. For that, we're going to use the dry lapse function. We're going to take our pressure plot and temperature. The mixing ratio. This one's a little bit more complex. We're going to calculate specific humidity using the specific humidity from a dew point function over pressure using our dew point. Then we're going to get the mixing ratio and we're going to use mixing ratio from specific humidity. And finally, we'll get the temperatures that we need to plot this mixing ratio line along using the dew point calculation, which takes a vapor pressure. So now we need to calculate vapor pressure, which we're going to do with our pressure plot array and our mixing ratio number. And finally, the moist adiabat. It's done with mpcalc moist lapse. And take our plot pressure and the wet bulb temperature. So not too bad there. Now we're going to plot our lines and data. And before that, we're going to plot general fiducial lines. So I'm going to plot dry adiabats. This is just the general lines that we have as the background on our Skew-T to sort of help guide our eyes. And I'm going to specify colors. Notice the plural here is going to be tab olive. And I'm going to set them to be very faint so they don't distract too much from our lines that we're plotting. We need to plot moist adiabats, and for those we're going to make them tab blue. And we need to plot mixing lines, and those are going to be tab green. Okay, plotting our special lines. Skew.plot, pressure plot, dry adiabat, color is tab olive, line width is equal to 2. Okay, and we know we've got 3 lines to plot. Moist adiabat is one. We're going to make that blue. And temperature mixing, which is going to be tab green. So let's plot this and see what it looks like. And this is what we would expect. So we take our wet bulb temperature, we follow a moist adiabat. Notice it follows the curve of these other moist adiabats that were plotted up on our Skew-T until we hit the LCL, which is where it is intersecting the dry adiabatic path of the temperature. And then we follow the mixing ratio line back down to our initial pressure, and we get our dew point temperature of not quite 13 Celsius. So this is a great way that you can create a graphical depiction of a rule like Norman's rule, and then actually check it with the calculations using MetPy. I hope that you found this useful, and I'll see you on next week's MetPy Monday.